First speaker is Narutaka from Kyoto. Tell us something about mathematics property for AutoCAD and DLS.
Thank you for giving me this opportunity, even though I have little to do with measured group theory or geometric group theory. In fact, I'm an operator algebraist working on C-star algebras and von Neumann algebras. So somebody says C-star algebras are an esoteric subject that most abstract nonsense that exists in mathematics. So this was a quote from Quanta magazine in 2015. In 2013, the computer scientists solved the long-standing open problem in operator algebra, Kazhdan problem. And it was featured in Quanta magazine. Recently, again, computer scientists solved the long-standing problem in operator algebra. That's a embedding conjecture. That's a kind of sophisticated problem for von Neumann algebras. So somehow we are attacked by computer scientists. And so I felt I obligated to return them, kick back them. So I solved some problem in computer science by operator algebra. So today's talk is about Kazhdan property T. Everybody loves Kazhdan property T, I guess. Kazhdan proved that lattices in the higher rank Lie group have property T, which I will introduce soon. And as a consequence, any lattice, higher rank lattice is finitely generated and has finite abelianization. Today, I assume from the beginning that all discrete groups, all countable groups I will talk about is finitely generated with some distinguished generating set. And then the property T is equivalent in this quantitative form that for any unitary or orthogonal representation of gamma, if the vector V is moved only little by the generating set, then it's actually close to invariant vector. Yeah. So the almost invariant vector is close to honest invariant vector, and there's a constant which depends on the generating set, but not depends on the existence of such constant is independent of the choice of generating set, and if such constant exists, then it's called Kazhdan's property. It has Kazhdan's property T. It's relatively simple, but not so obvious. But anyway, property T inherits to finite index subgroups, or in the case of locally compact groups, it inherits to finite covolume subgroups and also quotient groups. Quotient part is obvious because any representation of the quotient group is a representation of the original group. And the abelian group, infinite abelian group, does not have a property T. So this rigidity property is a generalization of generalized notion of finiteness. And finiteness has two generalizations to infinite groups. One is amenability, and the other is property T. And they are generalized into the perpendicular direction. So the intersection is finite groups or compact groups. So the other corollary that's Kazhdan, this was what Kazhdan was wanted to prove, that any finite index subgroup of property T group has finite abelianization. Yeah. And there's a lot of application of property T to measured group theory like cost and also geometry like expander. Right? Today I talk about expander graph. Expander graph is that it's a finite connected graph. I usually assume it's D-regular, simple connected. And it's called expander if any subset, the boundary is at least proportional to the size of A. But of course, if A is empty or X itself, then there's no boundary at all. So there's term which I don't know. There's which corrects the size of A. This is a remarkable property that the usual graph does not have this property, like this grid. Z-square grid does not have this property because this size is n square and the boundary is like size of n. And it has a lot of application because if it's an expander graph, then the k neighborhood always expands like exponentially until it hits the half of the population. Like this is what we have seen in the COVID pandemic, that COVID expands like exponentially up to some point and then decreases like exponentially. Yeah, but I guess our human graphs are somehow amenable, so it cannot expand until half of the population. Anyway, this means that the random walk on this expander graph is optimal one. It has optimal mixing time. That it's comparable to log of the size of x. And the expander, of course, we want to have a epsilon expander for fixed epsilon, and the size is arbitrary, and the degree is fixed too. The first explicit construction of expanders was given by Margulis. He used relative property, but in any case, it has group gamma is generated by finite set, and it has finite quotient, and we consider the Cayley graph or Schreier graph when it's a finite index subgroup of this S. Then this is an expander graph with constant depends on the Kazhdan constant of the group. So that this applies to property T group like SL3Z. And the generating set, we fix any generating set like ones on the diagonal and one at some ij's point elementary matrix. And the quotient is SL3Z over QZ. Then the question, then some problem happens that what if we change the generating set, but the group is SL3Z over QZ? Conjecturally, it's always expanders for some epsilon, give fixed epsilon. But for the simplest case is that the generating set, we change the 1 plus this 1, 1, 1 diagonal ones and one somewhere in the ij's position to the p in the ij's position, and p and q are relatively prime.
Right. Can you say what is the conjecture? What's conjecturally? Or
I don't know.
not necessarily.
The conjecture is that given any generating set of this, no matter what kind of generating set, there is a universal epsilon, that epsilon expander. But maybe generating set of the size 100 or d. Otherwise, it's the definition of expander may be a bit ambiguous. Yeah. And it's proven for SL2 by Fourier and Gamble. SL2 case it's special, and SL3 case already it's not known. Oh, SL2 case it's also the result is probabilistic, so that they know the such Qs have density, but not all Q. But this is much simpler, and actually, I will give you answer later. So the point is that the Q moves. If only Q changes, then it's expanders for fixed P, because this has finite index subgroup in SL3Z and it has property T. But I changed the P and Q both values, and I want fixed epsilon, yes, independent of PQ. Some examples of property T groups. So the typical examples are SL and Z, but not SL2. And this is generalized to EL and R. EL is an elementary matrix generated by I111 on the diagonal and R in the ij's position. Yeah. This is in the subgroup of GL and R. And if when R is commutative, the SL makes sense, and if it makes sense to ask if EL is same as SL or not. But if R is not commutative, there's no determinant. So I take this EL and R. And this has property T in full generality for any finitely generated ring. Now this R needs to be finitely generated, otherwise the group is not finitely generated. This was proved by Shalom and Wasserstein in the commutative case, and also Hayek in the plane in full generality around these years. Another generalization of SLM is that alt Fn, because Fn maps to Zn by abelianization, and so this actually suggests this induces map from alt Fn to alt Zn, but actually suggested by Nielsen's theorem that this has property. So the alt F2 does not have property T because SL2 does not, and it's a bit surprising or not surprising, I don't know. Alt F3 doesn't have property T neither because it has finite index subgroup with infinite abelianization, explicit subgroup. And it was open problem whether the alt Fn has property T, and it was solved by myself and Polish group. So Polish group appeared here. The proof is heavily computer assisted, and there's no human proof. So nowadays computers are getting stronger and stronger. I don't think computer starts to prove theorems anytime sooner, but because computer gets stronger in the exponential speed, you never know. But
yeah. So the proof you mentioned is based on your result about like you came up with some algebraic construct.
yes, I will talk.
And
Yes.
it's the same proof, yeah. So
yeah. So this is cockroaches. That in Japan we have a saying that if you find a cockroach in your house, only one cockroach in your house, there are 100 menu hidden somewhere already. So that's because they multiply exponentially. So I found one cockroach in my subject, so I found a problem which is amenable to computers. So probably hundreds are hiding somewhere around me. So the application to this auto Fn result is that it's used in computer science or computational group theory. That's a product replacement algorithm. A product replacement algorithm is that so the alt Fn, I take the SL, that's the determinant 1 case, which means that it's subject onto the SL2Z, the inverse image of SL2Z or SLNZ, which is by Nielsen's theorem, it's generated by right transvections and left transvections. That's so the right elementary transform, but the put Gj from the left and from the right are different when G is a non-commutative group. So it has left transvection, right transvection. And the product replacement algorithm is algorithm to random sampling in a given finite group. So you think think about that you are given a huge set and 4 or 5 permutations. You don't know what kind of permutation is it, and you are asked that what kind of group that these 4 permutations generates. Like if you are asked how you can estimate the size of this subgroup, yeah, then you do this product replacement algorithm. Product replacement algorithm that works as follows: that you apply this given generating set, you apply of the finite group, you apply this Rj, Lj randomly, and pick up random elements from here after n step. And practically, there are several random sampling algorithms, but the PRA is known to have very good performance. Practically, it's always very good. And the reason was not known, but the Lubotsky-Pak suggested that this PRA product replacement algorithm always works well because this group has property T, and this is a property T random walk, which converges first. And so this, because we proved its property T, in fact, indeed, we had a theoretical assurance that this PRA is always good.
But it works well for n equals 3 as well.
No, in case n equals 3, we just inflate this part that we put redundancy. here in the generating set. And in any case, you need to put redundancy in here. That's if there's no redundancy, these elements are somehow special. If there's redundancy, there's no specialty in the single element. And there's some problem about this, that it's supposed to have show the cutoff phenomena in probability, that's saying that it doesn't mix until some time, and it mixes suddenly well. And this is not proved, but anyway. Then I talk about the proof, how one can prove something like this by computer. That's it. I use theory which is called non-commutative real algebraic geometry. So that algebraic geometry deals with equations, but the real algebraic geometry deals with equations and inequations, because R is ordered field. Yes, so it deals with equality and inequality. So that for the typical example is Hilbert's 17th problem. F is a polynomial, actually a rational polynomial, and non-negative on the RD. And he asked if it's a sum of squares, if it's always non-negative. Hilbert knows that by existence theorem that Hilbert knew that this cannot be true for polynomial ring, but he wasn't sure about rational polynomials. And this was solved by Emil Artin in 2019 to 27. So this is a real algebraic geometry, and now we work on the non-commutative version. So I just replace this polynomial, rational polynomial ring with non-commutative ring. And then what positivity means? Positivity is that point evaluation is nothing but the unitary representation or orthogonal representation. So it's always positive semi-definite on the orthogonal representation. Then asks if it's a sum of squares. Yeah. Today it's particularly about. Today I work on real group algebra with the involution. But you need involution to. You need Hermitian sum to make it positive definitely always. Yeah. And the positive elements are those with sum of squares, but Hermitian squares, which is easy to compute in this case, which is nothing but the positive semi-definite matrix indexed by gamma, which is finitely supported under some of these forms. These are positive elements in the real group algebra. And if it's positive, then it's positive semi-definite in every orthogonal representation. And you want to ask the converse. The converse is usually not true, but you ask it in a certain specific setting. How one might solve Hilbert's 17th problem? I'm an operator algebra, I'm an analyst. So I still don't know if I can do this for what I say now. But because I'm an analyst, I would take a compression of this rational polynomials. Then I get a continuous function algebra. And continuous function algebra is non-negative, so I can find the square root. Yeah, square root is analysis. But the square root is not a rational polynomial, so I have to lift the solution, analytic solution, to a rational polynomial. Here I use perhaps a Hahn-Banach argument, Hahn-Banach separation. That's why there's a positive sums here. Now I do the same thing for this real group algebra. If I complete it with respect to natural topology, these representations, then I get this universal group Cis algebra. And because I'm a Cis algebraist, I can work with this easily and solve problem inside here. Then I need to lift the solution to here by Hahn-Banach theorem. Yeah. Today it's about the Laplacian non-normalized for generating set GAS. It's combinatorial Laplacian for gamma is the sum of 1 minus s star 1 minus s in the group algebra. 1 times 1 is 1 on the neutral element. 1 times 1 is 1. S star is S inverse. S inverse S is 1. So it's 2 minus S inverse. So it's like this. Why this is important is that I hit by vector v and take in a product, evaluate it. Then it's nothing but v minus pi s b squared, norm squared, summation. So this is close to 0, almost 0, if and only if v is almost invariant. And this is exactly 0, if and only if this is exactly 0, which means v is invariant under S, which means v is invariant under gamma. Yes, v is gamma invariant. So property T says that if this is close to 0, then actually the spectral projection of v to the invariant subspace has large component. Yes. In other words, in the spectral, in the term of spectrum, the spectrum has gap around 0 and around 0. It's always positive semi-definite. So 0 and the second spectrum lambda, there's gap between here. And this property is nicely formed in algebra. In terms of algebra, algebra is that the spectrum is 0, and here, if and only if delta square minus lambda delta is non-negative in the sister algebra by spectral mapping theorem. So this part is simple sister algebra analysis. And this solution actually lifts to a real group algebra or rational group Q gamma even. That's what I proved 10 years ago. And even nicer, that Netzer and Tom observed that you don't actually have to show that this is positive semi-definite. No, it's a sum of squares. If you can find a sum of squares, theta, which is close to this form, which you want to prove sum of squares, in terms of L1 norm, that's the summation of coefficients. And if this distance is smaller or 1/2 or much smaller compared to this lambda, then same lambda, then it has property T. Actually, this theta is close to honest solution, sum of square solution. So the this leads to a computer optimization problem in the computer. So gamma has property T if and only if that inequality holds in the group algebra, which means that delta square minus lambda delta is of this form written down in the positive semi-definite matrix, which is supported on some finite set E. If you fix finite set E, this is a problem which you can solve on the computer. So because if gamma has property T, you don't know if the solution is in the given finite subset E. But the given finite subset E, you can find the solution or not by checked by computer. So this gives you SDP problem. That's you want to maximize that delta square minus lambda delta is this positive form. And if lambda is strictly positive, we are done. By the way, I completely ignore the word problem. That's to implement this, you need to know which x inverse y's are same. But I ignore it because today our examples doesn't. It's easy to check in our examples. So the SDP is a generalization of linear programming. Linear programming that you have only linear equation and linear inequality. But here we are allowed to positive semi-definite matrix. That's positive semi-definite program. That's semi-definite programming. Linear programming, you can solve extremely huge problem by computer in a short time. And it's used in our daily life actually. But semi-definite programming, it's so far the algorithms are not so good. And you can solve the problem up to size of like million. So due to computer capacity limitation, so we almost always forced to take this E to be ball of radius 2, which is somehow minimum possible. That's its support of delta. Actually, even ball of radius 1, it makes sense, and it reduces to the Jukes criterion property. Ball of radius 2, it's better. And the size of SDP is like this, so that it's quite easily get million for groups we are interested in. And then of course computer algorithm does something black magic and gives you an answer, but it's not the answer. That the computer gives you some lambda note and p note saying that this is a solution, but of course it's not a real solution. P note may not be positive semi-definite. But then you can factor p note by square root and calculate that calculate this value L1 value with guaranteed accuracy, so that you either make it everything rational number and do the symbolic calculation. This is costly, or you use the interval arithmetics. And anyway, it's supposed to be rigorous, yeah, with guaranteed accuracy. If you prove this inequality, we are done. That's it has property T certified with estimate of Kazhdan's constant. Good part, there's a bad part and a good part. That's a bad part is that SDP is costly, so that it takes long time. It takes several weeks to a few months to solve it. But the good point is that the certifying process you are given, so that in the paper it's attached with this Q certification, Q and so on. So the certification is easy. That's it can be done on your desktop computer. Yeah. So this is slippery. I think that if some theorem is proved in a huge computer in some lab and only verification can be done on the same lab, then I'm not sure if it's rigorous anymore. It's somehow like natural science more, you know. Oh, but in any case, I think it will come like that soon. Yeah.
What's the number of variables in this, say, for out F4?
Out of 4, it's more than million. It's 10 million or like that. So the results that people implemented this algorithm for SL and Z, and computed Kazhdan's constant. So there was like Olympic game that people kept improving the Kazhdan constant of SL and Z. But the computer's calculation was 100 times better than human. So this Olympic game is over. Anyway, they did SL and Z up to n is 5. SL6 already problematic, but because it was huge, size was huge. And OTF4 it was already problematic because it has 10 million. But Karuba, Novak, and I tried it with Polish supercomputer. Use Polish supercomputer to factor the problem, make it simpler problem by modeling out the symmetry. This has huge symmetry group that's like 1,000 size of several thousands, and divide by this and symmetrize it and make problem simpler. And then they put it in the usual lab computer.
This
And-
Polish supercomputer, is it a mathematical term or like
No, it's real Polish supercomputer, Polish grid computer.
Okay.
And we tried AutoF4 first. Actually, they tried AutoF3 too for sanity check that if it has property. But fortunately, the computer doesn't say yes. And AutoF4, unfortunately, computer gave us no response after a long time. It didn't converge because we believe that you need to take ball of radius more than 2. But if you look at the value of Kazhdan's constant on the ball of radius 2, this 3 case it's much worse than 4 and 5. This value is improved if you work on the ball of radius 3. SL3 case, still you can work on the ball of radius 3 because SL3 is small. In that case, this value greatly improves and almost close to the, we believe, real constant. So perhaps ball of radius 2 is too small for this group. So we proceeded and got the answer fine and with nice constant after several months. Now, so the n equal 5 case is solved. N is more than 6. It was solved by Kalbakirak and Novak. By stability technique, that's what I talked about property T verification. You can do it one by one. You cannot prove infinitely many at once. So they needed some mathematics here. N equal 4 case, another SDP method is invented by Nietzsche in 2020 and was confirmed as property. So I think the proofs are more rigorous than human proofs now. Because there are different implementations and they gave us similar results, property. And some people reacted like Picasso like 60 years ago. 60 years ago, Picasso famously said that this is authentic in his interview, said that the computers are useless because they can give you only answers. That when he was asked that in his cubism, he do the calculation lot and somebody interview asked him, then the computer can do the picture. And he said computers are useless, but nowadays we know that computer can write the pictures well now. But in fact, I want to make the point that we worked like this and this because of the previous implementations told us they didn't say why it's true, but they said how one can verify this. Yes, and we proceeded and we didn't give up here and we proceeded because previous implementation told us that fair to look at and so how to look at and fair to look at, and even produced a new stability technique by Kalbakirak Novak. That's what I explain now. So this is technical. I don't want to talk about. So one wants to prove this beautiful inequality delta square dominates the delta. That's the property T inequality. But to prove it, they decompose the inequality in some arbitrary way. And arbitrary way, and I don't know what they actually did, but because I was not involved. But they put many things in computer, and computer answered some of it was true, and what computer said was this ad hoc ugly inequality is true. And then one can build the proof of that inequality out of this. But the problem is that after I was told the result, I looked at this inequality and tried to understand what it means, and I didn't find any meaning at all, human understandable meaning at all. Just it can be used to prove that. So that's what computer does. Yeah. So they produce something we don't understand. And it was before this COVID pandemic. 2019 December, Karuba came to Kyoto, and we discussed mathematics. Karuba and I discussed mathematics, and Karuba taught us gave me very important piece of information that they were able to prove this for nice alpha and nice epsilon. If alpha is smaller, it's better. But when Marek Karuba put a huge alpha into here, if its alpha is huge, then the one can prove this group has property for large enough n. For large alpha, computer immediately said yes to him. So the SDP is usually takes several weeks or a few months. But if you put a huge alpha here, computer immediately said it's yes. So this computer taught us very important mathematics that this strange inequality is not only true, but easy to prove if alpha is large. And I was lucky that this was before pandemic, because otherwise we don't discuss things like this on the Zoom. And so it may be easy enough for human to prove this inequality for alpha large enough. And the AutoFM case, I tried a little bit. So that if I prove this for alpha large enough, then I prove the AutoFN has property for n large enough. But some combinatorics were inhumane. That's we should not perhaps follow computers. Right? We are not computers after all. So instead, I apply this KKN method, this inequality to new setting, ELNR, with R is a ring. Ring is a proper mass term. Yes, ring is a ring subtracted identity. Identity is removed from ring. So that it's an ideal in the unitization. And the universal commutative ring is a polynomials in x1 to xd with zero constant term. Yeah, no constant term. This group may look peculiar, but it's not that peculiar. Actually, it appears as a parent group, like for a group like this, ELNPZ. This has property T because it's a finite index subgroup in SLNZ. But P varies. It's not. This group does not have uniform property T. That's a Kazhdan constant is not uniform. It's get worse and worse. Or otherwise, SLNZ, N is fixed again, but the generating sets are SPQ, it's a EIJP, so one's on the diagonal and the P only in the IJ's position, and one's on the diagonal and Q in the IJ's position, and PQ coprime, then it obviously generates SLNZ. If the Kazhdan's constant is uniform when P and Q varies, this is surprisingly it's not known. And anyway, it's conjecture that SLNZ is uniformly Kazhdan, meaning that Kazhdan's constant is universal, independent of the generating set of size, let's say size of B. And the simplest case is like generating set like this, but it's still not known. The problem is that if you want to apply outer product technique, you have to work with the outer product of this group, outer product of this generating set. Then you your ring is no longer unital. Yeah. You cannot make one out of PQ if varies. And in fact, ELNR has a huge, large abelian quotient. Just R over R square is abelian group, zero product. Or R over RK is nilpotent. So this is not uniformly property T because it has larger and larger finite abelian quotient as P goes. But then the moral of the talk is that my result is that still you can prove the uniform property T-type rigidity result by proving some substitute of property T for ELNR, but which must avoid the nilpotent quotients. If you avoid the nilpotent quotient sneaks in somehow, then you get a rigidity type result. So there are a lot of unsatisfactory parts in the theorem that first of all, my ring is commutative for some reasons. That's the Ershoff and Hykin's theorem that the R was arbitrary, not even non-commutative. The non-commutativity is important that you can put the matrix inside, right, in the matrix. And the N is large enough because I use that method and alpha is large. I can estimate how N is large, how large N is, like million or something, I don't know. Then this satisfies Kazhdan's property T inequality, but the delta is a delta Laplacian for ELNR, and the delta 2 is a Laplacian for ELNR square. R square is not R, yeah, smaller. And the inequality holds only in the sister algebra, in the analysis, not in the group algebra, not group ring, that's RELN. So the current method of computer doesn't prove this. You need analysis now. And as a corollary, that's if you go to finite quotients, these problems disappears, and so the Cayley graphs of Q and P both varies epsilon expanders.
Does the lambda depend on the theorem?
Oh, lambda is similar. You get similar estimate as theirs. What?
How absolute is that it depends on the group?
You fix n large enough and generating set D, number of generators, then there's lambda. Finally, I talk about a little bit about the proof. So this sum of squares method doesn't work in this case, and my proof is silicon free. Anyway, I can't use code. I don't write codes, etc. Instead, I relied on the Bock and Zaharevsky's work on the analysis. It appears in math physics that the almost Matthew operators on the rotation algebra, and they studied in detail about the spectrum of it, which results in the representation theory of the integral Heisenberg group. This is, of course, a nilpotent group, XY, and the commutator is central. In this group algebra, sister algebra, Laplacian for this Heisenberg group, XY, Laplacian was 1 minus x star 1 minus x plus 1 minus y star 1 minus y. Square dominates the Laplacian of this square, R square, H, that it's a nilpotent part, yes, central part. This is encouraging that one can put this several places in this group and do some analysis. And again, this inequality with even arbitrary constant is never true in the algebraically, never true. This is analysis. Yeah. Okay, that's what I wanted. Okay, thank you.
Any questions for Taka? Or any further complaints about computer science? I saw.
So applicant is just methods for other groups like mathematics.
Which, what group?
Applicant is simulation programming for say some small mathematics.
That is, I'm not a computer person, so I don't do that. And anyways, problem there is that mapping class group, etc. was that is that you don't have a nice generating set. That's in OTFN case, generating set is somehow canonical, and canonicity means that it has a huge symmetry. There is a huge symmetry. You can exchange IJs and you can flip it several here and there. Huge symmetry means that it's perhaps good to find a solution. And in fact, you can factor out by symmetry and work on that. Mapping class group, you don't have that, and also the problem is that it has a part that you need to solve the word problem. Word problem is easy for automorphism group. That easy means it grows super fast, but anyway, in a short length up to 4 we need only. Easy because we just apply this element to the free basis and look at what the free basis one gets, and if it's same, then the elements are same. So this part has no dispute, I guess. But mapping class group, it's already difficult to distinguish elements. And even if you code everything into if you even make a code and run and you get the result, nobody would believe in you. There may be bugs in doing that. Okay, yeah.
Okay, I just like the remarkable, about the work problem. So you would like your group that you're working with to have at least some kind of an automatic structure ideas to write down these constraints, yeah? Ideas, but even automatic structures can be done individually. So this year,
Yeah. Is there an narcotic or representation theoretic version of your almost property key? Your substitute property key?
No, I don't know. But you can do, but you can find it, no. Algorithmic, yes, there should be something there because it has something in C star algebra or von Neumann algebra, so algorithmic theory is already very close to it.
Do the n and the epsilon in the corollary come from the Woodford product, or in the last page, the n and epsilon in the corollary?
Epsilon, one can get some precise estimate up. This is same as this part is say what independence of n is same as OTFN case on the SLN case. That's it's not depends on P. No, it's almost same as just Q case.
Okay, so before finishing our therapy session and meeting at 10:30 again, let's thank Taka again.